Hello to everyone in Playa Online Congress. I hope you and your families are doing good in the current situation. My name is Juan Pablo Arango. I am a researcher from the National University of Colombia, and today I want to share with you our research called Global Sensitivity Analysis of Passive Solar Systems, a case study in cold equatorial climate conditions. Let me begin briefly explaining what we propose and why we carry out this research. We propose an attachment of a greenhouse-type device on existing and new construction buildings for improving indoor thermal comfort for homes located in high mountain climates in a tropical latitude. In this research, our objective was to find the critical design variables of this device that have the greatest impact on indoor comfort. Why we did this research? Firstly, because of the lack of knowledge about this topic in cold tropical areas. Second, we want to be able to simplify the design process, helping architects and engineers to make better design decisions. Also, we want to encourage the use of passive design strategies in tropical areas, where there is a big potential to improve indoor comfort conditions. And finally, to be able to create tools that support earlier stages of design. How we carry out this research? We implemented a parametric environmental analysis workflow plus a global sensitivity analysis using Grasshopper, Python, Energy Plus, and R. Then let me introduce some general information about the construction site in Colombia. Buildings in Colombia are not climate responsive. Furthermore, communities located in cold mountain climates do not consider active or passive heating strategies for improving indoor comfort conditions, leading to low comfort for most of the inhabitants. Therefore, we propose a greenhouse-type device that aims to improve indoor comfort conditions and that can be easily attached to existing constructions. However, how can we know how to optimize and simplify the design process for the implementation of this device, especially in a location like the high mountain tropical climates, where the implementation and research about the topic have been very limited? In this study, we used the global sensitivity analysis, which helped us to recognize the most effective optimization strategy applied to a specific context. For instance, here we use the enhanced sensitivity analysis method of Morris, considered as a computationally inexpensive method of analysis with very good results. Let me introduce the analysis process. First, we take the input variables and define the range of analysis. Second, we define the output variables that we want to measure the model with. Then, we sample the design space for creating a sensitivity analysis case. After the sample, we can set up and run all the simulations with a parametric workflow. And then, finally, we can carry out post-processing of the results. Let's see more in detail the methodology we implemented. We started creating the sensitivity analysis case with R. Then, we carried over this list of cases that needed to be simulated. Here we use the Ladybug Tools plugins for creating and automating the simulation process of all the cases. Then we send the simulation files to Energy Plus and OpenStudio. And finally, we read back the results to R to be able to post-process the sensitivity analysis. We carry out a case study located in the capital city of Colombia, Bogotá. Bogotá has nearly constant weather conditions as a result of its low latitude and elevation above sea level of roughly 2,600 meters. Temperatures on the nights are very low, reaching values lower than 8 degrees Celsius. Despite the cold weather condition, it's not common to use active or passive heating strategies. As we can see in the image on the right, the thermal model consists of a small box representing a bedroom located on a second floor of a typical countryside house in the area, with similar constructions, geometry, and spatial arrangement. In this case, we can see that the attached greenhouse as well as the thermally massive wall, the latter in red color. This led me to my next point, which are the input variables and the analysis ranges. In this research, we analyzed a total of 10 variables, including orientation, the size of the greenhouse device on its 3 axes, the U value of the glass, the material, size, and thickness of the thermally massive wall attached to the existing exterior wall. Additionally, we studied the thickness of the roof insulation, and finally the internal gains. We carry out a total of 165 simulations for this study. Let's now turn to the output variables. We define the output for the thermal model in terms of percentage of time in comfort and operative temperature for night hours between 6 p.m. and 8 a.m. in the morning. To assess the thermal comfort inside the space, we use the adaptive comfort standards from ASHRAE 55. For this location, we find out that the comfortable temperature range could be between 19.6 degrees and 24.6 degrees, depending on the season. I will now like to move on to the algorithm that makes all decoupling possible. We use Grasshopper 3D inside Rhinoceros for the integration of the simulation using Honeybee plugin, which lets us create and define the thermal properties of the model. It also allows us to automate the simulation workflow between Energy Plus and OpenStudio. And that's all about methodology. Let's explore the results. In this slide, we can see one image per output metric, where all the variables are sorted to display the most important ones at the top. On the left side, we can see the result for the percentage of night hours in comfort, where the variable with the greatest variation is the people's internal gains, as shown an average variation of almost 30%. Additionally, the width and the height of the greenhouse device plays a crucial role in comfort performance with a relative variation of more than 15% in this metric, even more than the greenhouse materials or the orientation. So we should prioritize the size of the device before focusing on the construction materials of the same. On the right image, we can see that the results for average operative temperature have a similar ranking to the previous metric, showing a maximum variation value of 2.5 degrees for internal gains. Now let's look at the remaining metrics. On the left, we can see that for minimum operative temperature, the main change is the thermal insulation of the ceiling, rising to a second position of relative importance, as shown by the variation in the metric close to 2 degrees. On the right image, we can clearly see changing the device orientation is the most important variable, with an impact close to 2.5 degrees. This may be due to direct solar gains that hits up the exterior wall, having high temperature values at the beginning of the analysis period. In conclusion, based on our findings, we consider that the top 4 highly sensitive design parameters identified using the enhanced Morris sensitivity analysis method are people internal gains, the width and the height of the greenhouse device, and changing the material of the roof insulation. Therefore, we will recommend to architects and engineers to consider these 4 variables as a critical for the design of the greenhouse type device for homes located in high mountain climates at tropical latitudes. Some of the next steps involve implementing a prototype device onto existing building, improving the thermal model assumptions, exploring the cost-benefit relationship compared to other passive or active design strategies. That brings me to the end of my presentation. Thank you for listening and stay safe.